Hello students, this is Kashima Soni and today we are going to take up our next topic, that is factors affecting the magnitude of crystal field splitting or 10 DQ values. So this is in the series of your crystal field theory only. This topic belongs to that particular series only. So if you guys have not checked the video of crystal field theory postulates, crystal field splitting in octahedral and tetrahedral complexes, and how to calculate the CFSC in both of these complexes, you need to check that. Only then you will be able to understand the factors affecting 10 DQ values. Otherwise, you are not going to understand anything that we are going to discuss today. Okay, so I'll mention the link. I'll paste the links in the description box. Go check that first and then come to this video. And yeah, so let's start with the same. Correct. So proceeding further, we have over here, you can see, okay, the four factors that affect crystal field splitting energy. That is, first one is going to be the nature of the ligand, and here we are also going to discuss the spectrochemical series, which is going to tell you which one is the stronger ligand and which one would be your weaker ligand. Okay, and then next factor is oxidation state of metal, another one is type of d orbital, and the last one would be geometry of the complexes. So we'll be taking each one of these one by one, talking about the first one, that is your nature of ligand. Okay, so before jumping to that, let me clear one thing to you. Okay, and this is your splitting in case of tetrahedral complex. It is E and it is T2 orbital, and splitting in case of your octahedral is more than in case of your tetrahedral. And what is the reason for that? That is what we are going to take into account. We have actually discussed that in the previous slides as well, in your previous lectures that I have pasted before uploading this one video. So go check that out wisely and then come to this video. Okay, you'll unable to understand then only. Okay, sorry, this is your EG and this is going to be your T2G. Okay, and the splitting in case of your octahedral is more as compared to tetrahedral. That is what we are going to check the reason. What are the factors, which are the reasons which is responsible for such kind of splitting. So yeah, let's see that one by one. First is your nature of ligand. So greater the ease with which the ligand can approach the metal ion, greater will be the crystal field splitting caused by it. तो कहने का मतलब यहाँ पे क्या है कि जितनी इजिली आपके लिगेंड अप्रोच कर सकते हैं मेटल आयन को, उतनी ही ज्यादा स्प्लिटिंग होगी. अब ऑक्टाहेड्रल की बात हम जब कर रहे थे कि उसमें स्प्लिटिंग ज्यादा है, तो ऐसा क्यों है? क्योंकि जो मेटल के ऑर्बिटल्स हैं, मेटल की जो डी ऑर्बिटल्स हैं, दे आर लाइंग इन द डायरेक्शन ऑफ योर इनकमिंग लिगेंड. Okay, and if they are lying in the direction of incoming ligand, what will happen? Greater repulsions will occur, okay, in between the electrons of your ligand and your metal, already present electron in metal. Greater repulsions will occur, which leads to your greater splitting. So now you understand, जितनी easily आपके ligand approach कर सकते हैं metal को, उतनी ज़्यादा crystal field splitting होगी. So this is one of the reason आपके octahedral में क्यों ज़्यादा splitting होती है. ठीक है. Then next is your ligand, which can cause only a small degree of CFSC, your crystal field splitting. ऐसे लिगेंड जो क्रिस्टल फील्ड स्प्लिटिंग स्मॉल लेवल पे करेंगे वो वीक फील्ड लिगेंड होंगे, जो आपके लार्ज स्प्लिटिंग करेंगे ligands वो strong field होंगे. Okay, that is important concept, you should keep that in mind. Another one would be your, okay, spectrochemical series I'll take up after discussing the ligand, after this discussing about all the ligands that are responsible for greater crystal field splitting, and then we'll be taking up the spectrochemical series. So the ligands which can cause greater crystal field splitting, because स्मॉल लिगेंड्स, ओके, स्मॉल लिगेंड्स जिनका साइज, ऐसे लिगेंड्स जिनका साइज स्मॉलर है, दे कैन कॉज ग्रेटर क्रिस्टल फील्ड स्प्लिटिंग बिकॉज दे कैन अप्रोच द मेटल आयन very closely, right? And we have taken the example of fluorine. Fluorine is going to have more CFSC value as compared to your chloride and bromide ion. Okay, that is one example. So keep this thing in mind. Smaller the size of your ligand, more would be the CFSC. Okay, the another point would be ऐसे ligands जो आपके easily polarizable electron pair हो जिसमें, they are also going to draw your metal ion more closely, and if they are going to draw the metal ion more closely, so ultimately splitting would be more, right? Another point would be The ligand which have greater tendency to form multiple bonds such as Cn negative and NO2 negative, it can cause greater crystal field splitting. ऐसे ligand जो आपके multiple bonds बना पाए जैसे कि Cn negative और nitro group that is NO2 negative, they will be causing greater crystal field splitting. The very high splitting produced by Cn negative ligand is almost double. देन फॉर द वीक लिगेंड, जितने भी वीक लिगेंड होते हैं उनके कंपैरिजन में आपके सी एन नेगेटिव की जो CFSC वैल्यू होगी इट वुड बी मोर एज कम्पेयर टू हेलाइड आयंस. ओके, दिस इज ड्यू टू द पाई बॉन्डिंग इन दीज मेटल. पाई बॉन्डिंग आपको पता है आपके CN का कैसे आपका स्ट्रक्चर होता है, समथिंग लाइक दिस इज सिग्मा एंड 2 पाई बॉन्ड्स आर प्रेजेंट ओवर हियर, यू कैन सी. So this is attributed to the pi bonding in the metal, correct. So metal donated electron, यहाँ पे आप एक्चुअली आपका बैक बॉन्डिंग का कंसेप्ट भी आ सकता है कि मेटल जो है, मेटल आपके अपने फिल्ड T2G ऑर्बिटल से भी डोनेट कर सकता है इलेक्ट्रॉन अपने इस लिगेंड के वेकेंट ऑर्बिटल में. ओके, उनके कोई ना कोई p ऑर्बिटल वेकेंट हो सकता है, तो वहां पे बैक डोनेशन का केस भी आ सकता है. इफ यू वांट टू रिमेंबर इट, इट इज गुड, यू शुड एक्चुअली कीप दिस इन माइंड. दिस इज अ क्वाइट अ गुड पॉइंट to remember. Okay, another point would be the following pattern of increasing sigma donation is observed, which is by which they mean अगर आपके पास कोई ऐसे लिगेंड है जिसमें कार्बन डोनर प्रेजेंट है, उस केस मतलब कार्बन डोनेट कर रहा है अपने इलेक्ट्रॉन टू द मेटल डी ऑर्बिटल, तो क्या होगा उस केस में CFSC सबसे ज्यादा कार्बन डोनर वाले की होगी एज कम्पेयर टू नाइट्रोजन, एज कम्पेयर टू ऑक्सीजन, एज कम्पेयर टू हेलाइड. दिस इज द पैटर्न. ओके, कीप दिस इन माइंड, दिस इज वेरी इंपॉर्टेंट. You can see in the next slide. Yeah. So you can see the effect of CFSC of the ligand attached to the chromium 3 ion. This is your chromium having 3 oxidation state in all of these complexes, and first one would be your where carbon is the your carbon is your what it is your donor. Carbon is the donor atom, sigma donor atom over here. So what will happen, it is going to have greater CFSC that I have explained you in the previous slide only. Why? Because we have observed this sigma donation pattern, basically carbon, then nitrogen, then oxygen, then halide ions. Okay, halide including fluoride, fluoride, bromide. That is it. So nitrogen, we have these two values. Now you'll ask why the nitrogen, the ligand having NH3 is their CFS is lesser as compared to the ligand ene, because this is your strong field ligand that you will see in your spectrochemical series, and this one is your weak field ligand. Correct. So that is one point, which is why the strong field ligand is going to cause greater splitting and ultimately going to have greater CFSC value as compared to your ammonia ligand. Okay, then we have O donor atom, that is H2O, the molecule that is H2O. Then we have your halide atoms F and Cl, F being smaller in size causing greater crystal field splitting as compared to your chlorine. That also we have discussed in the previous slide. So listen all the points that I'm saying very carefully, only then you are going to understand what is the factor actually, how they are affecting your CFSC value, correct? So proceeding further, let's discuss about the spectrochemical series. Okay, so when your ligands are arranged in the order of increasing crystal field splitting, it is that particular series is known as spectrochemical series. It could be asked in 1 marks in your subjective paper, so just keep this thing in your mind, right? And the ligands which are present up to ammonia, up to here, they are all weak field ligands. These all are weak field ligands. Okay, your halide ions and then these NO3, these oxalato ions, all of these are weak field ligands. While the ligands which are present to the right side of your ammonia, ethylene diamine, then nitro and Cn negative, CO, these all are very strong field ligand. Correct. So it is clear that CO, Cn negative, NO2 negative, they are strong field ligand, whereas your halide ions are weak field ligands. Correct. So that is one thing. Proceeding further to our next, okay, this is our next factor which affect your CFSC value, and that is your oxidation state of metal ion. Alright, so taking the same factor, we see the metal ions which have higher oxidation state, they are going to cause greater crystal field splitting than the metal ion with lower oxidation state. Listen to this point once again. ऐसे metal ion जिनके पास oxidation state ज़्यादा है, उनकी crystal field splitting भी ज़्यादा होगी उनकी वजह से, ठीक है? as compared to the metal ions इनकी lower oxidation state है. And the example that we have taken of hexa aqua cobalt, having one of the complex having cobalt in +3 oxidation state, having CFSC value 18,600 centimeter inverse, where one of the complex where cobalt is in +2 oxidation state, having CFSC value 9,300 centimeter inverse, almost half of the this complex where cobalt is in +3 oxidation state. So this is one example which clearly shows you your more the oxidation state of metal, more is the splitting, more is the crystal field splitting. So we have a chart over here where you can find out various other example of the same. So yeah, you can go through it and you can remember any of the value, and while you are describing it particularly in your paper, you can take up any particular complex and give the example. Yeah. So next point would be your type of d orbitals. They are going to say over here is when your metal, when your the extent of crystal field splitting for similar complexes of metal, when the metal is in same oxidation state, it will increase on going to from 30 to 50% on going from 3D to 4D series, and this increase is almost the same amount on going from 4D to 5D series. So कहने का मतलब क्या है कि जैसे आपके जिन जिन ऑर्बिटल्स का साइज सबसे ज्यादा किसका होगा 5D का एज कम्पेयर टू 4D एज कम्पेयर टू 3D, greater the size, greater is here greater the size of orbital, greater would be the splitting. Okay, size of orbital I am talking about. Okay, not ligand. So greater is the size of your orbital, greater would be the crystal field splitting. Remember this much only, you will be able to answer your question very easily. Yeah, so 4D is bigger as compared to 3D, and that is what I have mentioned. Then 5D is bigger as compared to 4D. So you can see what is going to happen. There is a particular example over here where your metal atom having cobalt, rhodium, they are the metal iridium, they all are in same oxidation state +3. Correct, they all are in +3 oxidation state. So on going from 3D to 4D to 5D series, you can see all of them, they are going to have the same metal atom with sorry, same oxidation number. Okay, and now but 5D being larger in size, 5D orbital, it is going to have greater CFSE value as compared to 4D, which is going to have greater CFSE value as compared to 3D. So that is all about it. Talking about the next point, that is your geometry of the complex, that is the last factor. So we have discussed already about the same in your previous videos, that crystal field splitting for tetrahedral is nearly half the value of octahedral. Why it is so? Because splitting in octahedral is to the greater extent as compared to CFSC for tetrahedral. Why? Because the coordination number for tetrahedral is lower as compared to coordination number for octahedral. Octahedral has coordination number 6 and tetra is having coordination number 4, which is why your splitting is also lower in case of coordination number 4 having geometry tetrahedral. And the value of splitting energy for tetrahedral complexes is smaller as compared to pairing energy. So that is why your tetrahedral complex is a high spin complex, that I have already told you in the previous slides. So yeah, this is all about it. I hope you have understood that well. And before ending the slide, before ending the video, I would like to request you all that इस टॉपिक पे डायरेक्टली जंप करने से पहले इट वुड बी बेटर आप क्रिस्टल फील्ड थ्योरी के पोस्टुलेट, octahedral complexes में splitting, crystal field splitting in octa as well as your tetrahedral complexes, go through that topics wisely, make your own handwritten notes, and then come to this topic. Then only you are able to understand the entire CFSE series. So yeah, that's all about it. And if you have any doubts, you can ask me in comment section. Thank you.